Well, here's what I can tell you about the quiz. You should make sure that you understand how to do the homework problems. All right? Because the quiz is very similar to one of them. All right? So the homework problems are the ones that I did on video. One of the ones I did on video is very similar to what the quiz will be. All right? Okay. So let's do another optimization problem.
Just quick curiosity, if we finish the Newton's method, I mean the 3 bonuses for the test are still on the table.
The 3 for the what? Newton's method?
Yes.
Yes.
Okay.
Yeah, I'm just extending the deadline. I'm adding more bonus to anyone who turned it in early, or today. All right, so I'm working 4.5. I'm going to do a problem right out of the book. I'm going to do what looks more interesting, number 23. All right, so number 23 says, I'm going to write it down. A right circular cylinder is inscribed in a sphere of radius capital R. Find the largest possible volume of such a cylinder. This is a classic Calculus 1 problem right here. Classic. So let's try and understand what's happening here. You have a right circular cylinder. Everyone know what a right circular cylinder looks like?
Just like a normal cylinder.
Yeah, it's a beer can, all right? There you go, right circular cylinder. It is being inscribed into a sphere of radius r. So you have a sphere here, and this sphere has a fixed radius of capital R. All right? So you're going to put this cylinder inside of the sphere and put it in there in such a way that it is what we call inscribed, which means that it must touch the edges of the sphere. So can you visualize the different ways you could do this? You could have perhaps this scenario. Your sphere is not changing, right? It's always the same size. You could have a very tall cylinder that would be narrow. And when it hit up here, it wouldn't go all the way to the top. It would touch up there, wouldn't it, somewhere? It would touch. And actually where it touched the top of the sphere, it'd be like a circle up there, wouldn't it? The entire can, the top of the can would touch the surface of the sphere. And then you would have on the same thing on the bottom, the same sort of thing happening. So there would be like a little air gap in between the two. Do you all see that?
Like a bead.
Like a what?
Like a bead.
A bead?
Yeah, like beads. Like a pearl. If you were drill through it, put on like
Oh, okay, yeah, okay.
like a lump.
Yeah. I could do it that way. I could do it where you would have a very wide cylinder, maybe something like this. Like that. Do you all see that one in there? And I could have pretty much every variation in between, or everything in between. So I could go and I could make it a very, very, very short cylinder. The shorter it gets, the wider it gets. Agreed? The widest it could possibly be would be the diameter of the sphere, though. That's the widest it would be. But what if it was the width of the cylinder? I mean, the width of the sphere. Then how tall would it have to be? 0. You couldn't have it. You couldn't have a cylinder in here that had the same radius as the sphere unless the height was actually 0.
Oh, okay.
Right? Because as you go out, look what's happening to these edges. As you go out, the edges are coming down, right, and pinching off into nothing. If you go in, they get bigger and bigger like this, and then they'd start coming in, right? And what would happen here? If the height of the cylinder was equal to the diameter of the sphere, if the height was equal to the diameter of the sphere, what would the width of the cylinder have to be? 0, right? It would basically become like a pencil, then it'd become like a wire, and eventually just become a straight line. Understand? Everyone see that? So if I can have all these different variations in between, then the question is, what's the largest possible volume I could ever get out of that cylinder? So like this has a volume, right? This has a volume. What's the best one possible? What's the biggest volume I can get? Everyone understand the question? Because if we don't understand the question, we can't do it. Yeah? All right. So I'm going to start writing some stuff down. What is it that I am trying to find? Maximum, minimum. Which one? Right? I want the maximum volume. I want the maximum volume of a cylinder. Which means I'm going to need a what? A volume function, right? I'm going to need a volume function. What we said last time is when we say function, we mean we need our volume to be in terms of a single variable. So can you tell me about the volume of a cylinder? Just in general, what's the volume of a cylinder? The volume of a cylinder, pi r squared times the height, right? That's the volume of a general cylinder. So you draw me a cylinder, if this is the height and this is the radius, then the volume of it is given by that. Unfortunately, that's not a volume function because it has two variables, r and h. So what is it at this point that I can start to look for that will help me get this in terms of one variable? Do you remember what I called it last time? The constraint, right? So what's the constraint here? What is the physical constraint of this cylinder? It's got to be inside the sphere, right? It's got to be inscribed in the sphere. That's obviously a constraint. I can't just let this thing be whatever it wants. It has to fit in the sphere and touch the edges. Okay? So we know the constraint's going to come from the sphere, but how? I need another equation, don't I? Let me see if I can come up with a constraint equation. Anyone have any ideas?
Would it be the volume of the formula would be the volume of the sphere?
The volume of the sphere what?
Minus the
Is that like 1/3?
minus the length of the circle, the height of the circle.
How would the volume of the sphere tie into the volume of a cylinder? Think about what is the volume of this sphere? Is it changing or is it fixed? It's fixed, right? So right now, if I say volume equals whatever, that has nothing to do with this cylinder. All I know is that this cylinder can't have a bigger volume, right?
The radius changes.
What change? The radius of the cylinder changes, not the radius of the sphere, though, right? What's the radius of the sphere? Capital R, right? Look at this right here. I'm using little r here for this one, using capital R for the sphere. Okay, so we can sit here and we can look at this and we can, try and figure it out. And that's why you take classes like this. So someone can show this to you for the first time and you go, oh, okay, now I know I can do that. Yes?
I know it might be too soon for this, but I was thinking that the diameter of the cylinder can touch the opposite corners of the sphere can touch the opposite corners of the cylinder.
Yes, you're definitely on the right track.
Oh, it's kind of off. Can you subtract the volume of the cylinder from the volume of the sphere and set that as a constraint that it has to be within that limit?
take the volume of the sphere and subtract the volume, or the other way around?
Yeah, the other way around, taking the volume of the cylinder, subtracting it from the volume of the sphere. And then that volume right there is what you're contained in.
That'll give us like a maximum that we can have, but it doesn't tell us when this is the biggest it can be. It would just give us a range. Okay, so this is the standard approach, and you're right onto it, okay? We take this imaginary sword, and we take our sphere and our cylinder, and it doesn't matter if I pick this one or this one, just any of those, and we slice this thing right down the middle. Okay? Slice your sphere, open it up, throw one half of it away, and look at that cross-section. What does that cross-section look like? A rectangle inside of a circle. Everyone understand that that's what would happen if we cut this? Okay, so let me draw this. I have my sphere, and inside of it, I have a rectangle. That's if I cut it right through the center. Agreed? All I need to do right now is come up with an equation, right? My constraint has to be an equation that connects little r to little h, right? Little r to little h. Because if I have an equation over here that has little r and little h in it, I can solve for little r or I can solve for little h. Agreed? Agreed? Okay. So let's start drawing some things here. I think you were talking about like the corner. Is this what you were referring to? Like something like that?
Well, it's just because what I noticed is that the sphere has no h in it. So,
Yeah, that's right. The sphere does not have an h in it.
so that means the height of the cylinder could be anywhere on that sphere.
That's right.
So that's why I was thinking that the straight line.
Let's talk about that height.
I guess a triangle.
In this problem, the way I've drawn it, when we cut it, the distance from here to here, right? This is h, right? That's h. The distance from the center, let's put a center in here. The distance from the center to here is what? Little r, right? Everyone agree? Okay. Anything else on this picture that you know for sure? The diameter. Oh yeah, so if I go from this point straight across to here, that's the diameter of the sphere. Or even if I go from here to here, that's the diameter of the sphere, isn't it? So I can label that what? Big R. Do you see it coming to life here? You see a triangle? Do you see this triangle? Do you know the little base of that triangle, the little tiny side? What's this tiny side? That's little r. I've got two sides of a right triangle. Do you know the distance from here to here? Half of h. Half of h. Isn't that half of h? Do you have an equation that connects little r and little h together? Yes, it's the Pythagorean, right? Pythagorean says that this should be little r squared plus this side squared, which would really be 1/4 h squared. Agree? That must equal what? Big R squared. Now keep in mind, big R is a constant in the problem. It is not a variable. They told you the sphere has radius capital R, it's fixed. They could have said 5 feet, and then we would just have a number there, right? 5 squared. But they want us to do this in general, so that our answer will be for any sphere. Okay, that's our constraint equation right here. We are free now to solve it for either R or H. And then we're going to take that back and plug it in here. Are there any questions?
Yes.
Yes.
Why is big R the halfway point?
Why is big R what?
Why are you calling that the halfway point? Like,
From here to here? Okay, because doesn't this go from the center of the circle to the edge of the circle? So it's the radius of the sphere, isn't it? Right. Capital R is the radius of the sphere. Yes?
Why is 1/4 h squared?
A squared, square this is r squared. Square that, you have to square 1/2 times 1/2.
Yeah, but it's got a square root of it.
And you square the h,
Oh, okay.
right? 1/2 h times 1/2 h is going to be 1/4 h squared. That's what it would mean to square that. 1/2 times 1/2, 1/4, h times h squared. All right. I get to solve this for either little r or little h, and then take it back here and plug it in here, right? And then I should have a function that has only one variable in it. What would you like to solve for? You want to do r? Why r? Any reason? You just like it, or do you have? It'll be what? Easiest because of the 1/4 isn't there? Is that what you're thinking? Okay, I like that idea. Any other reasons why r looks better than h?
Because it indicates the height of the, that you can just plug R right into the other one.
Yeah, look at what's over here, right? If I'm going to replace the h, then I have to solve for h, and it's squared, so I'll have to do a square root, won't I? If I'm going to solve this for h, I'll have to do a square root.
Whereas the other one will be
The other one wants r squared, which is right there. So I'm actually thinking r squared here because I need r squared here. So it's actually really nice to just solve for r squared. So if I solve this for r squared, I get capital R squared minus 1/4 little h squared, right? That's what that is. And now I'm ready to come back to this and replace r squared with that. So my volume is pi times, in parentheses, big R squared minus 1/4 little h squared, right? That's r squared times h. Is your volume now a function of a single variable? Yes. Wait a minute, what about capital R? It's constant, right? So even though it looks like a variable, it is fixed. So this is a function of h, isn't it? This is a function of h. So the volume is a function of h, and it is, let's see if you can handle this, pi r, capital R squared times h minus 1/4 pi h cubed. So all I'm doing is distributing an h through and distributing a pi through. Agreed? This is our volume function. We wanted the maximum volume of the cylinder. We needed a volume function. We got it. Now what?
Couldn't you just put that pi over 4?
Yeah, you could put pi over 4. You could also put 1/4 pi. It doesn't, and they're the same.
Yeah.
So now what?
Now we need to find the largest possible way.
Domain, right? Domain. This is key step. Domain. What is the thing I'm looking at when I'm talking about domain? What am I considering?
Well, it has to be bigger than
What has to be?
the volume.
H is the variable, right, in this problem? This is a function of h. So when I'm talking domain, I'm saying what are the restrictions on h? So what is the smallest h could possibly be? 0, right? If h is 0, you actually won't have a cylinder. That'll be that thing that's a flat, it'll just be a circle, a flat sheet. Actually, it won't be anything, right? So 0 would be the absolute smallest h could be. What would the largest h could be? 2r. Well, h was the whole thing, right? I erased it. Oh no, here it is. H is this distance, right? The most it could be, if it's going to be in the sphere still, is the diameter of the sphere, which is twice the radius of the sphere, which is 2 capital R. So I can do closed interval method on this. The smallest would be 0, and the largest would be 2 capital R. Understand? That's my restriction on h. Now I take a derivative. Derivative, this is a polynomial function, right? H is the variable. I'm not doing product rule here, right? R squared is a constant. So what is this derivative going to be? What is v prime of h? What? Pi capital R squared is a constant. Cover it up. It's coming for the ride. What's the derivative of h? 1? Pi capital R squared. Okay. Minus 1/4 times pi is a constant.
So
3/4 pi. So the 3 comes out, hits the 1/4 pi, 3/4 pi, h squared. And I'm going to now take that and set that equal to 0. And I get pi capital R squared minus 3/4 pi h squared equals 0. And I think I can do this pretty clean, right? This is just a number, it's a constant. And so because this is a negative term, I'm going to move it to the right side. So I get pi capital R squared equals 3/4 pi h squared. And then what? Yeah, let's get the pi's out of here. We're going to have enough pi in a couple of days, right? Y'all ready for?
Multiply by 4, divide by 3.
Okay, so then multiply by the reciprocal of 3/4, 4/3. So I have 4/3 capital R squared equals h squared.
Square root both sides.
And then square root both sides. We'll have a plus or minus, but we can throw the minus out because h can't be negative, right? H can't be negative.
It's not even about me.
So we get from this, h must be, let's see, can we do the square root of 4/3? Isn't that just 2/√3? That's just the root on top and bottom. The square root of capital R squared is just capital R. And that's it. We need to plug that back in where? The original function, because we're using the closed interval method. We need to also plug in these two endpoints. So I'm going to go to my original volume function, which is here, or I can go back up here before I distribute it. It's my choice, your choice, right? But I need to now evaluate. I need v of 0, v of 2 capital R, that's weird, and then v of 2/√3 capital R. What did the question ask for? It said find the maximum volume, right? Or no, did it?
It did.
Find the largest possible volume. So it doesn't want the dimensions, it wants the actual maximum volume. So let's try v of 0. What is that? That's just 0, right? We plug in h is 0 here, h is 0 here, we get 0. How about v of 2r? I think I'll do that one over here. I'm going to write it down here. V of 2r. So I'm going to replace all my what's with 2r. All my h's with 2r. I like this one for some reason. I want to plug it into this one. I don't know why, I just want to. So I'm going to go here, pi. I've got capital R squared minus 1/4. Now what happens when I take h and square it? So what happens when I take h, which is 2r, and square it? What do I get? 4r squared. So this is times 4r squared, capital R squared. And then what's on the outside? Times h, which is 2r. Bless you. You okay with that? Do y'all see what happens on the inside of the parentheses? The 4's are going to become a 1. And it's going to be r squared minus r squared, that's 0. So you get 0 volume. But that's what we should expect, right? We were saying, look, if the radius of the cylinder is 0, you're going to have no volume. If the radius of the cylinder is 2r, then it's this big wafer that has 0 height to it. So you're going to have no volume. So this has got to be where the maximum is then. Because if those are both giving you zeros, then... But what is the maximum volume? Well, it's V of 2 over root 3 r, which is pi times capital R squared minus 1/4 times, now, let's square the h. So what happens when you square that? 4/3 r, capital R squared? Times h. But h is what? Two over root 3 capital R, right? So 2 over root 3 capital R. And so we have pi. Let's see, what is this in here? This is r squared minus 1/3 r squared. 2/3 r squared? And then this out here, 2 over root 3 capital R. Did I lose y'all? Y'all okay?
Why is that 2/3?
This is 1 capital R squared. These 4's cancel. That's 1/3 capital R squared. So 1 minus 1/3 is 2/3. I could go a little further. I could say something like 4 over 3 root 3 pi capital R cubed. I like that answer. That looks nice to me. All I did was multiply the fractions across the top, right? 2 times 2 is 4. 3 times root 3 is, well, 3 times root 3. I had a pi here. I had an r squared and an r cubed. What do y'all think? I'm going to check the answer. I haven't worked this in a while. 4.5. This was number 23. I'm going to read it out. 4 pi r cubed over 3 root 3. Okay, that's right.
Like the 4r squared comes from 4r squared.
Where?
The first one.
Right here?
First one.
Here?
Yeah. Right there.
Well, this is a separate problem. I'm plugging in 2r into this equation for h, right? When you plug it in right here, what happens when I put 2r right there?
Oh, you squared it.
I square it and get 4r squared, which gives me that.
You squared it already.
I already squared it.
Okay.
Yeah. And then the 4's go away. That's a 1r squared, and r squared minus r squared will give you 0. So if you have a sphere of radius capital R, and you wish to inscribe a cylinder into it, the largest such cylinder possible will have a volume of 4 over 3 root 3 pi r cubed, where r is the radius of the original sphere. Now, if it asked us for the dimensions, we could actually get them, couldn't we? We know the dimensions, at least we know this much. The h has to be this, right? And how would you find little r? If you know what h is, how would you find little r? To find the radius of the cylinder. Constraint. Go back to the constraint. The constraint has your relationship between little r and little h. For those of you, if anyone came in a little late, the take-home quiz, I've extended the deadline till Tuesday, but if you have it ready to turn in to me today, you can turn it in right now.
Will we still get extra credit if we do the Newton's method?
Yes.
Okay.
Yes. But talk to some of your classmates, because I started class out by going through and explaining, making sure everyone was doing it correctly. And I thought I was recording, but it was on mute. So, yeah. It's not part of this video. I stopped the video and restarted it. Do you want me to put up the video without the audio? Yeah? Okay. I will. All right. We're going to wrap up chapter 4 now. That's it for optimization. These optimization problems are a lot like the related rate problems in the sense that, you know, I can show you 30 of them, but there's still, you know, every problem is unique. The ones that I've assigned for homework, or the ones that are on your schedule, are all pretty much, you know, none of them really pushing the limits too much. I think they're all within reason. Some of the problems later in the section get pretty tough. So like the last problem you're supposed to do is number 25, but there are problems in this section that go all the way up to like number 58. So once you get into those 30s and 40s in the sections, those are tougher problems. Are y'all ready to move on? You don't care? Is anybody there?
We're just along for the ride.
Okay, you're just here, huh? All right, the last section of this chapter is called Antiderivatives. And this is where we start to begin to create a little bit of overlap between what you're going to see in Cal 2 if you take Cal 2. There's a lot of notes here, which I can go through, but I want to kind of motivate the idea with some examples instead. Let's say I tell you that the derivative of some function is 2x. Can you tell me what the original function was?
X squared.
X squared. Everyone agree? So if we're given this, we could be asked to find f, right? And so I heard the answer, well, of course, f of x must be x squared. Is that the only one that would have worked, though? What else would have worked? X squared plus 1 would have worked. So I'll put or x squared plus 1 would have worked, right? Because the derivative of that, the constant, the derivative of the constant is going to go away. It's not going to matter, is it? But by that same argument, it could have been an infinite number of them, right?
It could have been a different constant out front as well.
It could have been x squared minus 100. Not a constant in front, though. Not like 3x squared. That wouldn't have worked. Is that what you were saying?
Well, the original function of... Right. Yeah, I see what
What
you're
about like
saying.
146?
Yeah.
What's that?
Never mind.
No.
I see what you're saying.
Do y'all see that? That if you're given that the derivative of a function is 2x, the obvious answer is that the original function must have been x squared. But it could have been x squared plus 1, could have been x squared minus 1, x squared plus 100, minus 100, x squared plus any constant, in fact, right? Would have worked. So we have a way of writing that. What we do, these are all solutions. These are all correct, all right? But since there's an infinite number of correct answers, we want a general solution. The general solution to this would be to say f of x must be x squared plus capital C, where C is any constant. So here C is any constant. And we have a technical name for that C, which I'll introduce later, not yet. All right? Let's try something else. Oh, I forgot to tell you what the whole thing is called. This right here, all right, this right here would be the antiderivative. It's an antiderivative of the 2x. It comes from this, right? That derivative comes from this. So this is the antiderivative of it.
So an antiderivative is just basically a general solution for each derivative.
Yeah, it's the backwards process of what we've been doing. Instead of me telling you, hey, here's x squared, take its derivative, and you tell me 2x, I'm giving you 2x and asking you to tell me where it came from. I'm asking you to find what we call its antiderivative.
So it's basically like taking a step back.
Yes, we're walking backwards now.
So
Yes,
we were walking forward, now we're walking back.
that's right. That's right.
And then in Cal 3 we do somersaults?
No. In Cal 2 we walk backwards, but it's one of those things where you can only, you can only walk backwards really well if you can walk forward. If you have trouble walking forward, you're going to have a lot of trouble walking backwards. That's just the way it works. Okay, so let me give you another one. This time I'm going to write it just a little bit different. Okay, here's what I want you to figure out. Let's say that I give you some function. I tell you that the derivative of some function is x to the fourth minus cosine x. Can you find the general solution? So when you're going backwards, right? You think about what it meant to go forward. If you were getting two terms out, right? Like this, I have two terms in this derivative. That means they came from two terms, didn't they? You can look at it that way. What do I take the derivative of to get this? X to the fifth. Everyone agree x to the fifth, that the power would come down and become an x to the fourth. But the power came down though, right?
Where's that constant?
So I need to compensate for that. Why don't I put a 1/5 out there? Think about it. If I say f of x is, see if I just write x to the fifth, right now you could check it. Take the derivative of this. Do you get this? No, because the 5 is going to come out. You don't want that 5 there. So you scale it by 1/5. Now if I take derivative of this, do I get this? Yes. You see how that works? Now what about this one? What's that? Minus sine x. Because again, the derivative of sine x is cosine x, right? The minus will just come along for the ride. So that should work, right? Plus I could have any constant attached to this thing. I could have slapped any constant on there, right? We understand? Yes.
So when we find these, we don't need to have like a specific number for C.
No, you needed as a general, you need to put C.
Right, no, that's what I'm saying. Mm-hmm.
Yes. You need to just put C, but don't forget to put C. Because if you leave it off, then you're only giving one answer. There's actually an infinite number of answers, but see all of these functions, there's an infinite number of these, aren't there? Because I could add any C to this, so there's an infinite number of things I could have. But they all live in what we call the same family. I'll take you back to the problem we had before. Wasn't our answer x squared plus c? If I asked you to graph these, wouldn't this be like x squared plus 0 would be this, right? X squared plus 1 would be this. X squared plus 2 would be this. X squared minus 1 would be this. And so imagine an infinite number of parabolas, but they all belong to the same family of functions. They're all these x squareds that have been moved up and down anywhere. And if you really think about it that way, what we're saying is that if I go out to some value here, x, and I go to any of these parabolas, any of them, the slope of the tangent line is going to be the same at every single one of those parabolas. It's always going to be 2x. Okay, so we need some notation. We need some better notation, right? So we have new notation that I want to introduce. We call capital F of x the antiderivative of little f of x if the derivative of capital F of x equals little f of x. I should put notation / definition here. So when you look at least when I look at little f and capital F, when I think of that, I think of little f as the baby and capital F as like the parent, you know? Do y'all look at it that way or no? You don't? Aren't the capital ones like, you know, the bigger ones? Yes? So they're like the parents. The little letters are the little kids. So what we're saying here is that capital F is where the little f comes from when you take its derivative, right? So if you take capital F and you take its derivative, it spits out little f. In that case, we call capital F the antiderivative. I'm going to give you an example here. Find the antiderivative of f of x equals 2x. We've already done this problem, but the notation is going to look a little different here. What's the antiderivative of that function? X squared plus c. So here's how I write it. Capital F of x equals x squared plus c. See? This is the parent. When you take its derivative, right? When I take derivative of this, I get back that, don't I? Find the antiderivative of 2x. Any questions on that notation or the definition? All right, let me give you another one. Find the antiderivative of f of x equals the square root of x plus the cube root of x plus the fourth root of x. Ooh, okay. Now we're going to start trying to freak you out a little bit here. Not the derivative, right? I'm not asking you to take derivative of that. I'm saying this is the derivative of something. What? What was capital F? Where did that come from? That's the derivative of what function? So what do you think we can do that might help us here a little bit?
Put them in the 1/2.
Yeah, let's convert this little f over to rational exponents, just so we can have a look at what the powers of these really look like. This is really x to the 1/2, right? Plus x to the 1/3 plus x to the 1/4. Agreed? Now, what we learned earlier in the semester, and we've been using it a lot, is this power rule that said when you take the derivative of something to a power, the power comes out and you subtract 1, right? But if we're going backwards, we're going to have to add 1, right?
So that means that we have to find a common denominator for all of them.
No, we can leave them. We can do them separately. We can just do, like, let's find the antiderivative of this one, antiderivative of this one, antiderivative of this one separately. So what do we know about this capital F of x? Can you tell me anything about that first term? It's got to be x to what power? 3 halves, because you just add 1 to this, right? 1 half plus 1 is 3 halves.
Wait, wouldn't the front have to be 2?
And then we have to consider, if this is it, let's try it. Take derivative of this. Do we get that? We get, the powers are correct, but we're going to have a number out front that we don't want, right? 3 halves is going to come out. This doesn't have 3 halves. It's a 1, so what do? Do the reciprocal, 2 over 3. You see that? 2 over 3 out front. Now take the derivative of that, just mentally in your head here. Mentally in your head, I guess that's kind of redundant. Yes. Is there any other way to do it mentally than in your head? You understand what I mean? Does that work? Yes, that does. Okay, let's try the same for that. What would the power have to be? The power on the x? 4/3. So we add 1 to 1/3, we get 4/3. I'm going to leave myself a little bit of space here. I know it's going to be an x to the 4/3, but when I do this and it comes out, it's going to have to be a 1 out front, right?
So it's going to be 3 over 4?
3/4. And plus there. What about this last one?
4x to the 5/4?
See, x to the 5/4 here, and we're going to need out in front of it 4/5 plus, right? Plus c. Well, there's got to be a more efficient way. Maybe not. Let's see. I'm going to give you another problem. Same instructions. Find the antiderivative. Let's do this. 1 over that, 1 over that, 1 over that instead. How does that change the problem?
This makes them negative.
It makes all these exponents negative. Okay? If that's negative, and that's negative, that's going to change this answer completely, isn't it? Okay, so let me, is it all right that I'm just like adding on top of this one? Is that all right? I'm just going to erase this. Okay, same procedure though. Add 1 to that. You get 1/2, don't you? So this is going to be x to the 1/2, and then what do you need out front to counter off the power? Just 2. Right? This 1/2 would come down, hit the 2, and become a 1. We'd subtract 1 from that, we get x to the negative 1/2. How about the next one? What's the power on x going to be? 2/3. So negative 1/3, you're adding 1, 2/3, and then out front, 3 over 2. Kind of get the idea of what's going on here? Next one. So add 1 to this, you get 3/4. So 4/3, x to the 3/4 plus c. I know there are Cal 2 instructors who will count the entire problem wrong if you forget c. I'm not one of them, but I will get mad. I will get upset.
That's if we have you.
But I only get upset because other people are going to get really upset with you. So I don't want to act like I didn't care. I do care. It's an important thing. All right. Y'all seem okay with this? So far? Okay, let me give you this problem.
Is there a shortcut?
You know what? The way we're doing it is kind of the shortcut. We have a formula for it. We do have a formula, but if you just get stuck using the formula, it kind of, I don't know, to me it's, you want to just look at it and be like, hey, I know I need to add 1 to that, right? Okay, and then I know that I'm going to have to kill off that thing in front, so I do the reciprocal of it out front. Have you noticed that what goes out here has always been the reciprocal? Okay. But I'll give you the formula in a minute. I just want to see how you're going to handle this first.
How does that work out if the constant in front of the isn't like a 1?
Yeah, and don't worry, we're going to do more. Baby steps. Baby steps backwards. And then we'll be moonwalking at some point. Now some of you might know this just by looking at it, you already know what the answer is, but let's see what would happen if we try and convert this to x to the negative 1. It's not going to work, is it?
No.
Because you're supposed to add 1 to that, right? Capital F of x should be x to what power did we say? Add 0 and then,
It would be a 1.
oh, that doesn't work, does it? It doesn't work?
It's a logarithmic.
That's right. You just need to remember that the derivative of natural log of x is 1 over x, right? So you just need to know that. Natural log x plus c. So that rule that we were using for the powers, that rule works as long as the power is not negative 1. If the power is negative 1, the rule doesn't work. If the power is negative 1 on this x, then the answer is natural log. And that leads me to what's called the power rule for antiderivatives. If little f of x is equal to x to the n, then capital F of x should be, I should have to add 1 to that power, right? Now, just write this for a second. I'm going to write a brace like this. There's actually 2 things that could happen here. It could be x to the n plus 1, right? Add 1 to the power, but then we have to take care of that power out front. So how do I kill off an n plus 1? When it comes down, I don't want it to be there. So what do I put out front? The reciprocal, which would be 1 over n plus 1. That's being multiplied out front. Plus c. Do y'all see that that's all this is what we've been doing the whole time. This is true if n is not equal to negative 1. So as long as the power is not negative 1, like this one right here. See how the power is negative 1 there? If the power is not negative 1, we will use the formula. If the power is negative 1, then what? What's the answer? ln x plus c. This is the general power rule for antiderivatives. All right? So our power, you remember the power rule for derivatives was this one. But see, we're going the other direction here. So the n comes out, x to the n minus 1. Right, that's the power rule for derivatives. But now we're going backwards, so we have a new rule. It's for antiderivatives, and that's it right there. So let's try an example where our numbers get a little bit messier. So how about this? How about 4x minus 3x squared plus 7 roots of x over x cubed. Yeah, that's good. I want to find the antiderivative of that.
I guess convert those into the negative.
Yeah, what does your instinct tell you? Do you think that I'm going to be able to just say, hey, what's the antiderivative of this, this, and this, and then separately the antiderivative of this? Why don't you think that's going to work? That didn't even work with derivatives, did it? Like if I want to take derivative of this, you would have to use the quotient rule. You couldn't do this, 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 just take derivatives of each one and that's your answer. So, and you're correct. If you can't do that with derivatives, going backwards, you definitely can't do it. So we are not allowed to take the antiderivative of each one separately. because this is a quotient. What we can do,
Can we make it into one derivative?
we can rewrite these as this over this, and this over this first. Rewrite it. So I just wrote, since I have 3 terms on top and 1 on the bottom, I'm allowed to split it into 3 fractions. And now I just use the properties of exponents. No rules here, no calculus yet. This is all algebra. What is 4x over x cubed going to be?
4 over x squared.
4 over x squared, which I can write as 4x to the negative 2, right? That's what this is? 4x to the negative 2? What about this one?
3x negative 1.
Minus 3x to the negative 1. And the last one is going to be plus 7. You're subtracting, right? Isn't this 1/2 take away 3? What is it? Negative 5 over 2. X to the negative 5 over 2. Y'all understand I haven't done any calculus, right? This is just algebra at this point. I'm just rewriting little f. This is another version of little f. Looks different, doesn't it? I took x to the first power over x cubed. You do 1 minus 3, get negative 2. Here, 2 minus 3 is negative 1. Here, 1/2 take away 3 is negative 5 halves.
And now we can take it.
Now you can do the antiderivative of each of these. Now you can. So now, because I have 5, I have 3 separate terms, so I can take the antiderivative of each term separately. So capital F of x. Hey, with derivatives, what happened when you had constants attached to functions with derivatives? They came along for the ride. Well, guess what? They get to go for the ride when you go backwards also. They're going to go for the ride. So you see this 4 right here? When I go back up and do antiderivative, it's just going to come for the ride. Here it is. There's that 4, right? Because it would have just come with us, wouldn't it have? If we took derivative. So if we're going back, it's going to come with us. Now just cover up that 4 and give me the power rule on that. So what's the new power on the x going to be when I add 1 to that? X to the negative 1. And what do I need to put out in front of this to counter that negative 1 from coming down and changing the sign of that? I need negative 1 out front. Right? Look, negative 1 is going to come out, hits this, becomes what? Positive 1 times 4, it's going to be positive 4 out here. And then I subtract 1 from that, and I get negative 2, which gives me this. Do the next one. Negative 3 comes for the ride. And now do the antiderivative of x to the negative 1.
X is 0.
ln x. That's the special one, isn't it?
3 ln x.
So minus 3 ln x. I was covering it up for now. Next one, cover up the 7. So I'm going to have 7 here. And now do the thing on this. What happens when you add 1 to this? You get negative 3 halves. So my new x is going to be x to the negative 3 halves. What do I have to put out in front of this? The reciprocal of this, right? So negative 2 over 3. Oh man, I kind of ran out of room there. Okay, let me clean this up. It's kind of ugly. Question? No? Okay, so this is what I have. I have negative 4, x to the negative 1 minus 3 natural log x, and then minus, over here, 14 thirds, because I just multiply 7 times negative 2 thirds, negative 14 thirds, x to the negative 3 halves. Plus c, thank you. Plus c.